Okay, question. Anyone has any question? Yes, please.
Solve 1.5, number 8.
Actually, 1.5, we haven't covered it. We will cover today. Can I answer after we just do the main examples? We will cover today, and then we can practice for more examples with your question, okay? When is the due date for those homework?
Today.
Oh.
Can you make it tomorrow so we can look back today?
And then when is the test? I think I need to move it to the this is May 4th, we have time. This is chapter oops, 17. Okay. Okay, if you don't have any question on 1.23, actually 1.1 and 2, that's the only thing we covered. We need to do 1.3, but you have tried 3 problems. You won't have problem with this because we tried many examples last class. The whole class before the break was practicing this type of problems, okay? But 1.5, no, 1.5 is interesting. It's a little bit different and it's a little bit more interesting problems, okay? I have first combinations. As I said, we tried combinations. We know what is the combinations and we tried it. So the combination is the one that you can either write it in the notation of this NR or RN, or you can use it with the, what was the other notation? Or this one. So we tried many examples in previous class, okay? So today we want to try the permutation. What's the difference between combination and permutation? In permutation, the order matter, right? If you reorder it, it will change. It will make a new choice. So the order in permutation matter. In combination, the order doesn't matter, okay? So that's why you have more choices. In permutation, the order matters. It's like just writing a word. So if you reorder the words or reorder the numbers, it creates new numbers, okay? So that's why the order matter in the permutations. This is an easy example. It says if you have to rearrange the like saying letters, right? So if you have to rearrange letters, objects, maybe numbers, like saying you have always 6 permutations if you can have only the letters of A and B and C. If you're given only 3 letters, so you can make 6 different permutations. As you see, it's listed over here. So how we can count that many? So you just say, I have 3 letters. For the first place, I have 3 choices. You can put either A or B or C. So you have 3 choices in the first place. In your next place, because you choose one of them, you have 2 more letters to choose. And the next place, if you have already 2 of them, so you have one left choice. So that's why the product rule gives you what we call 3 times 2, 6 many permutations, okay? So when we are talking about the permutations, it has to really mention repetition matter or not. Do I have repetition or it doesn't? So this is, for this case, when you choose the first place to be either A, B, C, you won't have any more that choice. So then the next one, you have one less choice, okay? So then repetition in the problem directly must say, does it have the repetition or it doesn't? So for us, In this problem, it doesn't. That's why it's 6 permutations. Does it make sense? So this is a rule. This is a rule. It says if you have exactly n elements, means n letters, maybe n numbers, maybe n objects, n colors. If you have exactly n different elements, so the number of possible ways or permutations are always n factorial without any rule or any condition. Okay, so only the number of possible ways to permute those n elements is going to be n factorial. Okay. So one simple example. How many permutation you can make from the letters of A, B, C, D, E, F? 6. So again, you're having 1, 2, 3, 4, 5, 6 place. In first place, you have 6 many choices. Since you already choose one of them, 5 left, 4 left, 3 left, 2 left, and then 1 left. So that's why it's 6 factorial. So you have 6 factorial permutations if you have exactly 6 different letters. Make sense? Always the question is, if I have repetition, if one of the letters is repeated, what should I do? So this is another example. How many different permutations if you're having anagram?
7 letters, right?
It is 7. You mean 7?
No, I'm saying there's 7 letters in anagram. That's what that's.
Yes.
Yeah, it's 7 factorial.
And then how about A's, which is repeated 3 times? How about A's, which is repeated 3 times? You can't have letter of like A, N, right? So you can't have 3 letters of A back to back, right? That's nonsense. So when we say 7 factorial is too much. Okay, because of that letter A is repeated, you have to make it less. The answer is 7 factorial. Divide by the number of repetition, because you have 3 factorials, because you have 3 letters of A repeated. So that would be the answer. It's 7 factorial divided by 3 factorial. So you have to make it less. It's too much, because A back to back can be in the first place, can be in the second place, can be in the third place. So that 3 factorials of changing is repeated. So you have to make it less. How? By dividing by 3 factorial. Then the question is, what does this mean? Let me just simplify and then I'll explain again. So you have a 3 factorial. You have a, what was it? 4, 5, 6, 7. Divide by 3 factorial. So then you can simplify 20, 120, 20, 120 times 7. 840. 840. Okay, let me make it one more example here. Mississippi. Huh? Oh, sorry.
My SS. Yeah, 3 S's.
Yeah, sorry. No, I was right. Yeah. Oh, yes. Mississippi. I have another I, right?
Yeah. Miss.
2 S's again, right?
Yeah, 2 S's. Yeah.
P, 2 P's.
Yeah.
Yeah. What do you think? How many letters does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So repetitions. The letters S repeated. S is repeated how many?
4 times.
And then what is the I's? 1, 2, 3, 4. And then what else? P. This is for P's, huh? Does it make sense? How it works when you have repeated letters. When you have repeated letters, you have to divide by those because that makes it the same. That makes it the same word. If you reorder those A's, sorry, here is S's or I's, it makes the same word. So you have to divide by those choices, okay? Make sense? How many four-letter words can be made from the letter A to F? How many do I have? A to F. A, B, C, D, E, F, 6 letters. With no repeated letters. With no repeated letters. What is it? 1, 2, 3, 4. How many choices in the first place? And then? Okay, so this is 360. 20, 120, yeah, 360. Okay. Do we know what this is coming from with this 6 only stopping at, what was it, 3? I think we know, right? So somewhere from high school, you are choosing. No? The formula, which is actually right over here. When you are having K permutation out of n elements, when you are having K permutation out of n elements, which n is bigger than, when n is bigger than K, okay? So yours here, 6 is n, and you're choosing 4. You're writing 4 permutations out of 6 letters. You're writing 4 permutations out of 6 letters. So the P stands for permutation, N is 6, and then you're choosing 4. I'm so sorry. So then you're having 6 factorial divided by 6 minus 4 factorial. So that makes it exactly what you have on top. So 2 factorial, simplify, that's a 2 factorial. Then your next number is 3. Next number is 4, next number is 5, next number is 6, divide by 2 factorial. And that's exactly what you have, okay? So you're making 4 permutations out of 6. So which is true if you are having any K permutation out of N, which N is bigger than K. Fine? Notation wise, if you like the other notation, some books may be using the other notation, like writing K this side, N this side is the same. And that was one notation. I think that's 2, right? What was the other notation for combinations? Yeah, we don't have that notation. Okay, that's only 2 of them. So one more time, here is choosing K objects out of n elements, then permute them. Okay. Question here? Any question here?
I have a question.
Please.
So how does this formula compare to the combination one? I know there's like an extra K factorial divided on the product. And then why is that fair?
That's a really good question. Let's just see what's that one. So this is what you said, n factorial, and then you have a k factorial, and then you're having n minus k factorial, okay? So that basically is going to be the same as permutation divided by k factorial. Do you agree? So since your combinations, which the order matter, has less choices because you divide the permutation by k factorial. Okay, so when you have permutation, you have more choices because the order matter, and then you divide it by k factorial. Okay, does it make sense? That's how they are related. One more time. Any question here? These are not really that much complicated, but I think they have a really, when the worksheet is due? Today? How much you're done by now? I haven't checked your discussion board.
Discussion only included me at 11 p.m. last night.
And then how about the rest of class?
You finished hours? Yeah, I haven't submitted it, but I finished it since last night.
Mhm.
Or morning, actually. I just
Yeah.
haven't submitted it.
But people need it, right?
I don't have my laptop. I can do it right now.
Yeah, do it. Those are really nice. As I said, that worksheet is really nice problems. It's really like test problems. So they are different types of problem that you need to know based on your high school information, and then whichever we've covered here. Okay. I believe you do have questions on the 5.5 in that list, and I'll tell you which one is from 1.5. If you haven't finished it, if you couldn't do it, that makes sense because you haven't learned it yet, okay? Maybe again, you check it online and you got it, that's fine. But I don't think even high school we cover this kind of problems, okay? So what is this kind of problem? It says stars. So stars stand for anything that is identicals. So go ahead. What else I have on top? Which part you're looking for? Am I right? This is fine? Only this one. Is that okay now? Sorry. Yeah. I'll see what's 1.4. Most likely we did cover in the examples. Okay. What's the title? I'll check it. Don't worry. So what is the stars? Stars is standing for any type of problems that you have identicals, like you have 5 balls, which are exactly the same. You have 5 maybe cards, which are exactly the same. So maybe 5 numbers, which just card on numbers or numbers on card, which are exactly the same. Okay, so when we say stars, it doesn't mean exactly stars. Like here in this question, it says cookies. They are exactly the same cookies. So they are identicals. So what does it mean? That means if you change it, if you check maybe cookie number 1, it doesn't matter with the cookie number 2. So they are identicals objects. And then when we say bars, it could be whichever thing that separate them, right? You can put them in separate boxes. You can give them to separate people. So whichever thing that separate those identical items, okay? So you can put them just maybe partitions between them. Like if they are 5 people, they are identical, you put the partitions between them. If they are 5 balls, you put them inside the bags. If there are 5 cards, you put them inside the box. So when we say bars, whichever things that make them separate. Okay. So let's say in this example, they are really similar. If you check them as boxes, and stars, they are really similar problems, all of this page, okay? So number 1, it says you have 7 cookies you have 7 cookies and you're supposed to give to the 4 kids. You have 7 cookies and you're supposed to give to the 7 kids. How many ways you can do? How many ways you can do? Let's say these are chocolate chips. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay. And then your kids, maybe it's A, B, C, and D. Okay.
Can you give all of them 0?
Mm,
Good question.
sorry, I didn't hear
Can you
you.
give all of them 0?
Keep
Does
up.
that count as one answer?
Can they have 0?
Yeah, can each one get 0? Yes?
Yes.
So.
In this problem, you okay?
That's what I'm asking.
Okay.
Yeah. What I'm asking, I mean, this is important. If
No, you have to give them something. You have
Oh,
to
okay.
get yourself empty and everything to be on them.
Okay, no, that's what I'm asking.
Yeah,
Because
no.
you can give 7 to A.
No,
or
no, no,
6
no,
to
no,
A,
no, no,
or
no.
5 to A,
Total
and it
total has
depends.
to add up to the 7 cookies.
You have to get rid of
A,
all.
B.
Okay.
A, B, C, D. Numbers on A, B, C, D must add up to the 7 cookies. No.
You said each one has to have 1?
No, they don't have to have one.
You can give them.
have at least 1 cookie, or can?
No, you can give.
Yeah, one of them can be 0, but the
Yeah.
rest can get more.
Oh,
Yeah, you can give 7 to A.
Yeah. Yeah, that's one case. That is one case. That's true. That's one case. That's a good question. That was a good question. Okay. What do you think?
You're laughing at.
840.
800. I don't have the answer. So how did you get to the 840?
Is 7 factorial divided by 4 factorial. Because the first kid can get 7 of them, it's one combination.
He can't get 7. That's what he said.
Yeah,
Oh, yeah.
and the same thing with permutations. Because we have to give the 7 cookies no
Mhm.
matter what, but it doesn't say that every person has to have a cookie. If it says that, it's gonna be combination, not permutation.
Okay, keep your answer. You said 7 factorial, divide by 4 factorial. That's all. Okay. So, and then you end up with the
840.
840. And then what was your explanation? Can you repeat again?
My explanation, it says we have to give away the 7 cookies,
Mhm.
but it doesn't say each kid has to have 1 cookie. Like the first kid can have 7 of them.
Mhm,
So
that's one
why
case.
it's permutation of 7 to 4. If it says that each kid has to have 1 cookie at least, it's
No.
not a combination. But
This is,
This is permutation.
That's a really good question. I mean, that was a good explanation. This is saying, what you're saying, you are just thinking about rearrangement of the cookies, but I have another choice. How about if you rearrange the bars? Your bars are just exactly what you're saying. You're saying, I'm going to just keep the bars all the way to the end and say all of these 7 cookies are sitting with the A.
Okay,
So we have 7 cookies for rearrangement, and we have actually 3 bars for,
but in this question, stars are cookies, not the kids.
yes.
Then we have to put the bars between the cookies, not the kids. So because the stars are cookies, not the kids. Our main
And
mission,
that's actually a good point,
we
because
have to
if
give
you-
away the cookies.
oh yeah,
not
so
the
then
kids.
what did you say? That I agree with that one. So what you said over here, you can put the bars over here.
Yes, because those are the stars, basically. not the
Okay.
bars. In this question, bars are kids.
Yeah, the bars are whichever separate the kids, whichever separate the kids. Actually, that's a good point, because that gives you the same answer. Actually, if you put the bars on top, it gives you the same answer. But let's just finish this way and then think about the other way.
And my only question is why they're separating kids? Because each kid has an individual already separated. Like 2 kids cannot share 1 cookie. How-
So just you can think about you having not the kids, maybe it's just really bags. You put them inside the bags.
For this question, like when you put the bars for the kids, what is the point of it? Because
To
2
separate
kids
them.
cannot share a cookie.
Yeah,
How we separate A and B?
that's exactly what I said. So you're exactly, because you can't have the cookies. So that means you can consider kit number 1 is a box, maybe it's a bag, and the kit number 2 is just something, just you can separate them. Whichever words that make them separate, that's all about the bars, okay? So according to this one, you have 7 stars and you have 3 bars. Do I have any disagreement about this number of stars and bars? To separate the kits, I have to put 3 bars because I have 4 kits, and to just have all cookies, I have 7. Do you have any question about this too? So my total selection actually is 10, 4 permutations. My total selection is actually 10 for permutation. I'm going to just put some example. Let's say you're having A gives 2 maybe cookies, maybe B has 1, maybe B none, and then your C has 1, 2, 3, 4, and then your next one, maybe the D, how many I have? 1, 2, 3, 4, 5, 6. I have 1 more. So this is one case. As you see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, total of 10 things that I have to just permute them. 3 of those are bars, and then 7 of them are the cookies. Whichever switching, it gives you a brand new choice, brand new way of distribution for these cookies. Do you agree with this one? If you want to just say, I have those placements like this, those places, I have 10 of them. Okay, this is one example. This is only one example. This is only one case, one example or one case. So I have total 10 things, including 7 stars and 3 bars that you have to permute. Agree with this one? So how many selection do you have? Either you have to put 3 bars between 10 choices, or you have to put, what else? What is another way of thinking about?
Yeah, the other side is 7.
7. Either is about choosing 7 stars out of 10 permutations place that you have, or choosing the place for 3 bars out of 10. Does it make sense?
Yeah, it's the same question as the bit strings.
But the only thing is we have to reward it. The only thing is we have to reward it in terms of stars and bars. So then it's going to be the same as bit questions that we have had a few times. Okay. Can we try one more time?
So that's not the same answer as the first one?
I don't think so, but I'm going to try it, because that is 10 factorial divided by 7 factorial, and then that makes 7 minus 3 factorial. So that would be 7 factorial. I have how many? 8, 9, 10 left. I have 7 factorial, 2, 3, 8, 9, 10. 2, 3, 1. That is going to be, can you count for me? Sorry, do you have calculator? 120 is much less, right? Can we try one more time? This is the example number 10. I'm going to leave it for now and do it after, okay? So because this is more challenging. Example number 10, let's just leave it and try the next one and then back to that one, okay? Let's do 11 with the same things, okay? Can you read the problem and tell me which one do you see as stars, which one do you see as bars? You're supposed to get the number of possible solutions with the equations, which is 1, 2, 3, 4, 5 variables, It has 5 variables, but addition must be 13. If you want compare to the cookies, if you want, you can just compare it with the stars and bars and tell me what are your stars and what are your bars.
X, show the stars and the plus.
The plus are the bars. So how many choices do you have? Think about if your x sub 1 was 13 and everything else was 0. That's one choice. Let's just make one example as x star and bars. So let's say you choose x1 to be maybe 1, 2, 3, 4. Then you put bar 1, 2, 3, 4, 5. Then you put bar. And then 1, 2, 3, you put bar. And then maybe none over here. Maybe how many do I have? 4 and 5 is 9. By 3 is 12. I have one more. So this is x4, this is x5, and then it's ending with the total of 13 dots. So how about now? Give me how many stars do I have? How many bars?
13 stars.
So I have exactly 13 stars. That's true. Those dots are your stars. And how many bars? 4 bars because of those pluses, right? 1, 2, 3, 4 bars because of those pluses. Actually, this question must be positive integers, or sorry, I should say non-negative. Non-negative. Because we don't, obviously, if we have a negative choices, that wouldn't be the answer, right? We have much, much more choices. So we want to be either 0 or positive. Either 0 or positive. Okay. Do you agree with my stars? What is the question? What's your question, guys?
Just trying to figure out whether it's 0 or not.
For this explanation that I have added, yeah, because like just you can have one of them to be 0, right? Or you can have all of them to be 0, only one of them 13. So that's based on the wording. If we don't add non-integers, that's not the answer because we have negative number and plus minus cancel out.
Explain the 4 bars.
So think about the numbers. The number of variables are x1 to x5, right? Think about you have 5 bags, and you have 5 bags, and you have total 5 boxes, maybe. So maybe partitions, whichever. So think about you have a total 1 box, and then your 1, 2, 3, 4. So this is where your x1 is sitting, x2, x3, x4, and x5 is sitting, okay? Then the total, somebody is just coming over here and gives you 13 balls. Total 13 balls. And it's just really open the box and just throw all of those 13 balls inside those partitions. So then you have a choice, all of 13 sits in the first place, second place, or maybe some of them is distributing in all of those boxes. So the permutations is happening is between balls and those partitions. So that's why you have total of 13 balls plus how many? 4 of those partitions. So that's why you go ahead.
So there was like, let's say like 8 variables, there'd be like 7 bars?
Exactly, always one less. It's always one less. It's always one less. Okay. So then your choices are 17. Either you're choosing 4 out of 17, which are your bars, which is the same answer, or choosing, 13 out of 17, which is the same answer. This is the first part. This is the first part. This is the first part. Any question about the first part? Does it make sense? How about if like a cookie problem, at least two cookies to one of the kids, right? Sorry, to all of the kids, or here it's, go ahead.
So you accept either one of those answers?
It is the
It,
same.
yeah, yeah. They are equal.
I'm sorry.
You can just put the 7 factorial divided by 4 factorial and 17 minus 4 factorial, which is the same as 17 factorial divided by 13 factorial, and then 17 minus 13 factorial.
Oh,
So that's why they're the same. Can we think about how about each of these xi's must be at least 2? You can't have 0.
so we're having freedom of considering that we change to 2, that means we have at least 10 reserved, right?
Okay. So if you have x1, then x2, and then x3, and then x4, and then x5, and then these are your bars, and then you already decided about 2 of them. You already decided about 2 of them, so you have no choice of those 10 many. So you have how many left? You have 3 left. So that's saying 13 minus 10 is 3 left. And then for the bars, how many bars do you have? Still the same number of bars. You didn't choose it. You didn't change your number of x's. Still you have 5 x's, which makes 4 bars. Still 4 bars for 5 variables. So that makes it what was it?
7, 4.
Or yeah. So either you're choosing 3 stars out of 7 possible choices, or you're choosing 4 bars out of 7 possible choices. That was a good one, right? So you can go back to the kids and try to say, okay, if your kids must have at least 1, what would be the number of choices? Can I go back to problem number 1? Can I make it a,
So the reason it's 7 is because you have to do the 4, right?
yeah, we add the permutations are total of 3 stars left plus 4 bars. That was original problem. So it's total of 7 permutations, which you can change the place. Can we go back to the first problem and then try to reword it, say, this is part A and this is part B. Must have, we can't have 2 of them, right? So let's say 1, right? If you're supposed to make, if you're supposed to distribute those cookies, but you want to give them at least 1 to all of them.
So you have 4 cookies already accounted for. So you subtract 4 from 7 to the total amount of cookies.
So you have total of 7 cookies minus 4 kids. So you already decided about 4 of them. You decided about 4 of them. So you have how many cookies left? 3 cookies left. So that makes your number of stars. I don't know why I just write the stars. Is 3 cookies. And then number of bars. Star, yes, 3 more. Still 3 bars because still you have the same number of kids with the 3 bars. So that makes it how many? Yeah. Now, can you think about the other problem? Problem number 10. Problem number 10 on this set of problems says how many 7-digit phone numbers, 7-digit phone numbers are there in which the digits are non-increasing? That means every digit is less than or equal, or actually it could be equal, less than or equal the previous number. Yeah, we can use it. One, two, three, four, five, six, 7. 7 digits, huh? I have 2 8s. Seems I have nothing from the 7. Then I got 1 6. Got 1 6. I have no 5. Then I have 1 on 4. Then I have 1 on 3 again. And then 1, nothing on 2. And then I got 2 of them over here. That's my example. Then you tell me what are my stars, and then what are my bars. You have 7 stars because
It's 7 digits.
you're supposed to choose 7. Yes, 1, 2, 3, 4, 5, 6, 7 stars because you have 7 digits. And then how many bars do I have?
9. There are 10 digits, so 9 bars.
9 bars because 10. Sorry, I can just write it like this. 0 to 9 numbers. 0 to 9 is 10. 0 to 9 is 10 many. I mean 10 many digits. 10 options, yeah. 10 selections, yeah, that's true. How many? 16. Either 7 or 9 bars, right? Either you can replace or permute your bars, or you can actually, if it wasn't that wording like non-decreasing, if we could really switch the place of 9 8 and maybe 2, it doesn't work in this way, right? So it does not work in this way. If you could have non-decreasing function, if you could have like just numbers reorder from 0, because the main problem, the main issue was 0 can't sit at the first, right? 0 can't sit at the first place. Okay. Question here? Any question? I can quickly look back to your worksheet to see which one is like this. If I can find it,
I have a question.
go ahead, please.
So if it said that it has to be decreasing every number, you can't have like 2 of the same ones in a row, how would that change the answer?
Let's say you mean 8 8 is not the case.
It has to be like 8 7 7 6 5 4 3 2 1.
That's a good question. I don't know. Let's just think about it. Let's think about it. If you're having 1 bar for I think that's fix this, right? Bars. If you choose to be only one, so that means that bar doesn't change the place.
But it's still the same solution.
Those bars does not change the place. No, that gives you only one choice, right?
You want two choices for that.
Two choices?
Because 7 digits and 9 numbers, so we can start with the 9 or 8.
Yeah.
Other than that, or actually 3. You can start with the 9 and increase.
You
to
see? Because then you don't have the repetition of the numbers, and you have only starting from 9 all the way to the 7 digits goes to the 2, starting with the 8 all the way to the 1, and starting with the 7 all the way to the 0.
So how would you write it?
As a, because we have only 3 choices.
Yeah.
And so the way that we can just write it is really choices of the 7 digits. 1, 2, 3, 4, 5, 6, 7. So then, as I said, because that's not repeated. I mean, when you don't have repetition, then you don't have those bars permuting, or bars are fixed. It doesn't change the bar, so it's only the numbers. So if you start with the 9, then your next number, that's one change. And then, I mean, it's not a good question actually, right? So this good problem, not question, problem. 7. And that gives you this, and then that's one choice, and then another choice, and then another choice. I don't think that is really good problem, because we don't have that many choices. Did I write correctly? Did I repeat anything? 9, 8, 7, 6, 5, 4, 3, and then 1, 2, 3, 4, 5, 6, 7. It start with the 8, ending with the 2, with the 7, ending with the 1. Actually, we have one more choice. 4 of them. We have one more choice. That's interesting. I'm thinking how we can write it as permutation, because we have 4 left. Huh? We have 4 left. That's really interesting. I'll think about it, because I'm thinking if your first place can have choices of, no, I can't. I was thinking if you can just say you're having 4 choices with the first place, because it's total of 7, and then 10 digits is there. So then your other places are really having 1 after you. I mean, if you decide about the 9 is sitting in first place, or 8 is sitting in first place, 7, or then what would be the next choice? It's going to be really 1 choice after that. Does it make sense what I'm trying to say? That doesn't work, but I should have one other way of doing this problem. Let me think about it. This was simple. Okay. I was just looking back to your, I'm going to move to the new section, but let's look back to your worksheet to see which one is connected to exactly this problem. And then when you're doing the problems, you know which one you must do. I think it's only 1 or 2 questions. This is, where is your worksheet? This is your worksheet, and then it's called worksheet number what? It's called worksheet number 7, huh? Not this one. These are not. Only 42. Only 42. For the seal, we can do it in any other way. We don't have to do it this way. Okay. Any question here? I had another question. You said what's 1.4? I'm pretty sure we covered 1.4 because of the problems that we tried it, okay? But I'll check it right now. Because I'm going to move to the new chapter. Any comment, question before moving to the new chapter? Again, you have really good set of problems in your worksheets. The worksheet number 7 or whichever is counting worksheet, you have really good set of problems there to practice all of these. I always have problem to find my textbook. Anyone has it? Oh, yeah, it's here. Your 1.4 is combinatorial proofs, which are this type of problems that we tried in the previous class. So these are exactly what we call combinatorial proofs. The one that you have to, this is one example. This is one example. This is another example. These are what we tried in previous class. These are 1.4. So in your book is making different sections, but it's just really, we tried it with the examples in previous one. Whichever identities that you have to show with the binomial theorem is called combinatorial proofs. But we can try it. If you need more example, I can try it in next class. Okay, now I want to move on my new section. I will try more examples after you're doing your homework. So I have really good set of examples after you're doing your homeworks, okay? The reason I want to start my chapter 2 because your first part of chapter 2 is something review from high school. You all know what sequences, even if you didn't pass your calculus 2, you know what's arithmetic sequences and geometric sequences. Am I right or no? Do we know what's arithmetic sequences and geometric sequences? So that's exactly the same thing. The first half of the sequence or chapter 2 is what I want to review from you guys for your high school, for you guys from high school. And then the second half is not repeated. You don't know it. The second, which is recursive equation, it's brand new. Recursive equation is brand new. So this is a review, but if you don't remember, that's fine because we are practicing, right? So we are just really bringing enough examples and practicing. And then the second half is our job, or it's brand new for this course, which is recursive equations. I have two sections over here. One of them is arithmetic sequences. The second one is your geometric sequences. And I try examples, and then I'm stop for recursive equation for next class. Come on. Any comment, any question, anything here? No? So what was the arithmetic one? So if I just bring one example for you, if you're starting with the 2, then plus 3 is 5, then plus 3 is 8, then plus 3 is 11, then plus 3 is 14. So arithmetic one is the one that you add one constant to get the next term, right? So arithmetic is the one that each term is coming from adding what we call, what was the D? What was the 3 that I'm adding each time? So we call it common differences, right? So you have a common difference. So each time you are adding 3 to get the next term. So 3 is your common difference for this arithmetic sequence. So for arithmetic sequence, you should have one initial term always given to you and one common difference. Then you can write the rest of the terms of your sequence. And for actually we have, for each of them, we have 3 formulas. One of them is recursive definition, so which says exactly what I said. Each term is coming from previous term plus the common difference, okay? And the other one is the closed formula, which says each term is coming from first plus D times N. So if you are standing in the 4th place, so you have to have the first one plus, what was your common difference? Times 4, right? So which is 40. So that's called closed formula. And then we have one more, which is the sum. That is 3 formulas for each of them. So for these two, we want to practice. What is the recursive definition? And what's the closed formula for these sequences? And then list, assume your first term is A naught, but this is given by list of elements. This is given by list of elements, okay? So for part A, what is A naught? What is the common difference? What was the common difference? Oh, just the 3. The common difference, 3, right? So then what's the recursive definition? So your, what was it? A.
Are you just asking us to use A and this one?
Mhm.
Yeah, that's three.
That's what it is, right? So then if you want, you can test it. Yeah, so you can test it. You say like A5 example or testing, okay? A5 equals A4 plus 3. Anyone has any problem with this wording, or maybe A sub n? What does it mean, A sub n minus 1? All of you guys remember what is A sub n? What is A sub n minus 1? You have no problem with that. When you say A sub 0 is your first initial term, when you say A sub 1 is the next one, A sub 2 is next one. So it goes really by your natural numbers, 0, 1, 2, 3. So because that's what you have, first term, second term, and your order is going to be just all positive, not negative. So this is, what was it? A sub 4, 1. What is A sub 4?
Zero, right?
What was it? You're starting from 0. You're starting from 0.
17.
So your A sub 4 is 14 plus 3. So 17, yes, exactly, your A sub 5. So your A sub 5 is 17. Does it make sense? That's how you go to the next step, recursive equation. What is the closed formula? Which is starting with the 2 you said plus 3 times, and that's it, right? Like just practicing what is A sub 99. What is A sub 99? 2 plus 3 times 99. Calculator? Yeah. So 299. Okay, for part B, initial term is 50. Common difference?
-7.
-7. How do I get it? You just really subtract these two terms, right? So any of these two terms, if you subtract, it gets 29 minus 36, or 36 minus 43, or 43 minus minus 50, which is -7. Okay. So your recursive formula or definition, which is this -7, is that okay? And then your closed formula is initial term plus, -7 times n. Initial term -7 times n. So one more time, what did I say in general? Your common difference is whichever term that you choose minus the previous term. whichever term that you choose minus the previous term, okay? Yes, please.
What's the difference between the two?
What's the difference between?
What do you use closed formula to find value? So what do we find that recursive?
Yeah, for recursive equation, as the name is clear, you have to back to the previous term. So if you want to have a 99, so you have to have 98. So you can't just get directly jump to the 99. So if you're looking for 99, so you have to have what is the 98th term and then plus 7 or, what was it, 3, right? So which makes more job, right? So you have to have all the way to the 98 and then add 3 to get. But for that's the recursive equation, means always the previous term was given and then you go to the next. But for the closed formula, no, you can jump to any term. That's the only difference. Go ahead.
A question following up on him. So if you were going to ask us on an exam to evaluate a number like on a recursive, say A77, do we actually, with recursive, we actually have to find every single.
Before 77, then you go to that one. Yeah.
So we probably won't be able to do that. We can keep it like that.
Yes.
Oh.
Yeah. Okay. Question here? For geometric, so for geometric, what's the difference? The only difference for geometric is you multiply by a constant to get the next term, right? So you always multiply by a constant to get the next term. Again, if you back your high school or whichever place that you've seen them, you saw them really in more complicated one. I don't make it that much complicated because what I needed here is the recursive equation. And I want to just adjust my equation in recursive form and just want to teach you how to solve any recursive equation, okay? So the geometric, as we said, you multiply each term by a constant, which is called common ratio. So this time is common ratio because you have to divide each term to the previous term to get your ratio. That's why it's called common ratio with the letter R. And then as you see, the recursive definition means you have to have the previous term multiplied by R. For recursive definition. For the closed formula, no, you can jump on any of them as long as you have the first term and as long as you have the common ratio. As long as you know what is your first term and common ratio, so nth term is going to be a times r to the power of n. And we're starting from 0. You don't have to, but here in this book, we start from 0. Okay. And part A, first term. First term is common ratio. Either is 6 divided by 3, or you can say is 12 divided by 6. Yes, is 2. Okay, so any 2 terms, you can divide it, right? So one more time. In general, how do I get it? It's going to be always one term divided by the previous one. One term divided by previous one. So then what is your recursive? Your recursive form is going to be an equals ratio, which is 2, an minus 1. And then this is required your first term, which is 3. And then for the closed formula, your an equals a times 2 to the power of n. 2 to the power of n. Is it fine? I think there's a mistake here, right?
Yeah. Either I'm crazy or it's missing a 3.
Yeah. Let's fix this one. If you start with the 27, the next number has to be 9, 3, 1, and then 1/3. Is missing 1, right? there was a mistake there. Okay, so what's your first term? And then what is your common ratio?
And
Yeah, so 1 divided by 3. 9 divided by 27 or 3 divided by 9, so it's 1/3. Okay, so recursive form, which back to the previous term is going to be 1/3 of the previous term, and then your closed formula is going to be your first term, which is 27, and then 1/3 to the power of n. Okay. Any question here? So, as I said, recursive, and then closed formula, and then sum. There are 3 formulas for each of these sequences. And for the sum, actually, we have had it. We know what is the sum. We tried it in induction once. We tried it by what was it? Combinatorial proof. And I'm pretty sure we tried it with that one in the one example. So this is actually the 3rd time that we see this kind of sum. This is the 3rd time that we see this kind of sum. We are looking to the elements only as the sequences, either arithmetic or geometric sequences, and then we follow the formula. So for arithmetic sequences, you should have the first point and the first term and the last term. If you want to get what is the sum of n term, you should have the first term and the last term, and you get the sum. The only challenging you might have is, if this is an example, I should know which n is 470, right? So again, I know what's the first term, I know what's the last term, but I don't know what is the n. That's the only challenging we have in the formulas. Which n is 470? Which formula gives you the n? Closed formula. So if you use your closed formula, and that would be an equals a n, what was it? Actually, a naught plus n times of d, am I right? So you're having 470 as your nth term, which you don't know what is the n. Yeah. Then your n is what you're looking for. The common difference. What's your common difference? 3. So then for the, what was it? 46/8, huh? If you subtract, and then if you divide by 3, you said is 156.
It's either 155 or 156.
Did you get 156?
Yeah, that's it.
Okay. So one more time. What I'm looking for is adding how many terms? $157. That's the point, right? You're adding 157 because you're starting from 0. Your first term is the 0, and then your last term is the 156, a sub 156. Does it make sense what I'm trying to say? Why you have to have one more? Because you start from 0. If you start from 1, a sub 1, yes, that's true. You are adding 156 numbers. But since you're starting from 0, it gives you 1 extra. So it's 157. Just whichever, okay? So you put it in calculator. Can we try one more? Find the sum of first 15 terms of this sequence. So the question directly asked me is sub 15. which is 15 divided by 2, first plus last. What's the last term? What is the last term? How do I get my last term? One more time, close formula. So that's again arithmetic. So your A, what was it? Close formula. AN equals A0 plus n times of D. Your A sub 14 equals A0 plus 14 times, what's the D? 5? Which is 71. Whichever number, okay, so you can put it in calculator. Fine. No more time, right? You have to stop here. Question. I have only the one more, I will say, for geometric, but my main job for this course is recursive relations, or how we solve for recursive equation. But still, if you need more examples, I'll try the next class, okay? So if you guys don't remember your sequences, we will practice more examples. So we're supposed to have one quiz today, right? The quiz, a quiz on counting, because I'm giving you a little bit time to practice on counting. So I have to, what did I do? I extend your homework first of all, right? So that was your homework that was extended to the next class. But how about the worksheet? Do you guys can finish it, the worksheet tonight or not? For the worksheet, I'll give you one more night because I want you study and then make the quiz on Wednesday. Is that fine? So can I? Quiz on counting on Wednesday, okay?
Answer about homework is still tonight, and it's about the whole chapter. It's about the whole chapter. So you'll be still due tonight.
No, I changed that one.
Oh, you changed the one?
At the
Changed
beginning.
to which day?
Next Monday.
What?
Next Monday.
Next Monday.